afternoon on this slightly cold and drizzly day. We're happy to provide some entertainment for those of you who can't go outside today. My name is Dr. Luke Donforth. I'm down from the University of Vermont where I work and teach. I've brought a lot of students and friends, and we're excited to share some science with you. So there are hands-on activities over there, but we're also going to do a little show here with some stuff. It's easier to show in kind of a big picture. Now the event that we're talking about today, Nano Days. Who's already been next door? I see some of you already have toys. Nano. What's the word that comes to mind when you hear nano? Let me just hear people call out some stuff.
iPod.
iPod Nano, all right? What else comes to mind when you hear nano? Cars.
Second, nanosecond.
A nanosecond. Good stuff. Is a nano big or is a nano small? Small. Nano, 10 to the minus 9, 0.000000001. On the small side. But those nano things, those small things can have big effects. And they're around you a fair bit. You might not always notice when you're interacting with things at the nano length scale. So I've got some light here, and light's great at illuminating some aspects of science. Joke there, I don't expect people to get my jokes though. So we've got white light, pretty straightforward, and possibly you've used a mirror before to redirect light and bounce it around, but we're going to redirect some of the light instead of all of the light. And so that white light, when I redirect some of it in different ways, what do we see? A rainbow. So do we have different colors there then? So those different colors have slightly different wavelengths, and so they bounce in different ways. Now that central area that was bright before, I've spread out some of that light so that I'm getting that rainbow of colors. So when we have white light around us, we have that rainbow, but we don't always see it because everything's coming together. It's only when we separate things out, when we diverge them, when we send them in different directions, we see those colors come out. Now this is the opposite of paint. Who here likes to paint or color? If you take all of your crayons in your 64 crayon box and add them all to the same spot, do you get white? Seeing some shaking heads. Who's tried that? You don't really get white anymore. So when you add a bunch of colors, it gets darker and darker. When you add a bunch of visible light, you end up with white light. And this happens not just with rainbows, but at other times too. And so here's a question for the adults in the audience. Who here has had or is worried about getting the question, why is the sky blue? Anyone had to field that one yet? All right. So we're going to talk about why the sky is blue. So we know that the light coming out of my projector is just white light. And I have here a model of the sky. So I've taken miles of atmosphere and condensed them down into this fish tank. Not quite, but something like that. And so, let's get the lights off again. When I send light through my fish tank, what color does that look to folks? Blue. Bluish. So we've got that blue color coming off of what was white. But now, let me turn the table so that you can stare down the barrel of the fish tank. And so you're looking down the fish tank at the light, and it looked blue before when you see it from the side, but now, what color do you see when you look down the fish tank? In the second row there, what color did you see? White. Anyone else see other colors in there? yellow. So it's not the same color. So I'm going to try and bounce some of that back. So is this color the same as that color? No. Kind of a sunset. So this is why the sky is blue. The sky, I've taken several miles of atmosphere and condensed it down into a fish tank. Do you believe me?
Yeah.
No, not quite. What I've done is added some coffee creamer, actually, to regular water. And the molecules of this, as it goes into solution, as it mixes into the water, the molecules scatter light. Scatter just means they bounce it in a different direction. And so for some of you, when you see it out this way, it preferentially bounces the blue light, which means if we've taken out the blue, we have the red left. So that's why the sky is blue. Things in the atmosphere. Now the atmosphere is not as dense as my fish tank, thank goodness. But there's still stuff floating around that preferentially bounces light. And it tends to bounce the blue light back towards you, and then you are left seeing that kind of sunset straight through. Now, we had a solar eclipse last night, or a lunar eclipse. And that lunar eclipse blocked out the sun from the moon. And who's ever seen a lunar eclipse? Last night was a little too cloudy for it. Anyone ever seen a lunar eclipse? Some of you. What color was it when you saw that lunar eclipse?
It was the orangey color and
The orangey color of the moon. So that's the sunlight making it through the atmosphere, being blocked a lot of the blue, and then that reddish orangey light reflects off the moon. So not only have we answered why the sky is blue, we've also tossed in why sunsets are red and lunar eclipses. Bonus service here at Echo. We're always happy. All right. Now, some of you probably came out for the bubbles. Were any of you excited about bubbles? A little bit of bubbling. All right. So I have a simple bubble solution here. Nothing particularly special. And what do you notice in those bubbles?
Rainbow and colors.
Colors. Everyone take another look. See if you can spot any colors in those bubbles. Good, you left it. So, we have colors. Now, this is a red tube. Am I getting red bubbles? So where does the color come from? Where does the color come from? The light. Because white light is actually lots of colors. Now, why is it, and some of you who've already been next door might know, why do we see all those beautiful colors in the rainbow, in our balloons? How thick is a bubble? How thick is a bubble?
Pretty thin, not really thick at all.
Not really thick at all. It's pretty thin. That's a great description. There's not a whole lot there. It doesn't block much light. It's a thin film. So the very thin wall of the bubble that lets light through reflects a little bit of light and lets other light through and then reflects on the other side. So if I have a wall and a wall, I could block all the light. But if I let most of the light through and reflect a little bit here, and then most of the light through and reflect a little bit here, I can preferentially get one color on this side and one color on that side. Now, if it's reflection and transmittance, if we're bouncing the light versus letting it through, if you see blue, what color will I see on my side of the bubble? Orange. So some of the light is being reflected back to you and you see one color. Some of the light is coming through and I see the complementary color. And all of these colors we see are built up of light with wavelengths of nanometers, hundreds of nanometers. Now, those are small bubbles. I want to make slightly bigger bubbles. Should I make slightly bigger bubbles? All right. So stay in your chair because the floor is starting to get a little slick and I don't want to hurt anyone. But let's try and do one more big. Now, even when I make them big and floppy and long, they tend to round themselves out. So we have surface tension. There's all sorts of interplays going on in that bubble that tend to drive it into different shapes. It's hard to make a bubble that's square. But you can see those oscillations, and there's all sorts of great physics happening in something as simple as bubbles. So we have thin films that interact with light in different ways, that build up reactions, and that's actually the same science at a fundamental level of what happens in a laser. So this is an old laser that we've taken apart, so it can't fire, there's no light that's going to come out. But you can see we've got mirrors on the ends, and those mirrors are tuned to reflect certain colors of light. And so we build up thin films. Now, this is not actually a mirror. It's a series of papers showing multiple layers. But we can tune mirrors by building up thin films of very specific thicknesses to act very well as bouncers. So can I have you five stand up right here, and you're going to stand in a line right here facing that. All right. Can I have you come here and hold this mirror? Okay. And can I have you come to this end and hold this mirror? All right. Now, my volunteers here are going to help model a laser for me. And the way a laser works is we have molecules of gas. Can you guys be molecules? Awesome. And we have a photon of light. And the photon goes back and forth, and every time it hits the mirror, it bounces. And so I'm going to bounce back and forth as this photon. Every time you see the photon go by, I need you to emit energy. Can you emit energy? Can you go whoop? Can you go whoop? What about you two? Can you go whoop? Can you whoop? All right, so every time you see the photon go past, as it bounces back and forth, I need you to emit a little bit of energy. You ready? Look at it that way. Here we go. Now, I am not as fast as light. In 1 nanosecond, 0.000000001 second, light can go as wide as, will go that far. We'll go about there. So every nanosecond, I need you guys to emit energy. Go! Give a big hand to our volunteers. That process of stimulating emission with a photon going by and creating more energy that goes out can work together to build a really big whoop, as it were. And so we build up lasers that give off light And we're going to show, get the lights dark, a pretty bright laser that we're going to poke up at the ceiling. So there's a nice bright spot on the ceiling, but you might even notice it's bright enough that it actually shines on some of that dark, or some of the dirt in the air. And so lasers have a very specific wavelength of that light, and they're kicking out that energy in a model of that process that we demonstrated here with our friends. Let's go ahead and get the lights back on. So now I have a balloon structure here. I've got two different balloons. I've got an outside balloon, I've got inside balloons. How well does the outside balloon absorb light? Can anyone see me through the outside balloon? Alright, so this structure doesn't absorb light very well. What about the dark balloons? Can you see me through the dark balloons? Not particularly well. So those absorb light. So we've engineered a structure such that one part doesn't absorb light and the other part does absorb light. And what that lets us do is target part of our structure. So I'm going to attempt to pop the inside balloon without popping the outside balloon. Do you think I can do it?
Yes.
Some yes, some no? Alright. We'll try the experiment. Physics is an experimental science. We do these things and then we try. We come up with our theory and we test it. And so let's see if we can pop that inside balloon without having an explosion of our outer balloon. So this is the small explosion if it works.
Aim it at that front balloon there.
Laser.
Alright.
Whoa, the laser.
So the laser shown through our clear balloon, absorbed by our inner balloons, and then that pops them. And this is the type of engineered structure that scientists work on doing. Now, you might think, oh, it's not super useful to pop inner balloons and leave the outer balloon. But similar things are done, for instance, in targeting cancer medicine, where you want to go after one thing or not something else. Or something as simple as your sunglasses, where you want to block one type of light, but not the other. And so these investigations into nanoscience or nanoengineering help us make these engineered structures to do what we want to do and not what we don't. So thank you very much for coming out and spending a little bit of your day with me. Thank you for coming out to ECHO. And if you haven't already, please swing by the activities there. We've got lots of hands-on things where you can play around, do some maybe take some things home. Have a great day.